Hello there, my name is Edera Wangui from Kodarasa. Today we're going to cover normalization in databases. So, what is normalization? Normalization is organizing data into multiple related tables to minimize data redundancy. So we introduce a new term here, that's data redundancy. Let's find out what data redundancy means. Redundancy. So data redundancy is repetition of similar data in multiple places, and we're going to see more on this. So basically you don't want that. This is cases where you're repeating data that you shouldn't be. You can find easier ways of not having it repeated as often, but we're going to see examples of this, so don't mind me. Anyway, so it does not eliminate it completely, but it does minimize it. This is something you need to be aware of. We'll still have cases of redundancy, but we are just minimizing it. So what are advantages of reducing data redundancy? Why should we do it in the first place? For one, it takes up extra space, so we need to reduce that space used, because at the end of the day we do care about data, we do care about space, we do care about cost, and even managing that data and analyzing it matters. So having it in a more organized and neater space is better for us. It's easier to understand. That's another thing. It's easier to enhance. We're going to see all these, why it's easier to understand, seeing examples of tables created without that in mind. And most of all, it protects our data from insertion, update, and deletion anomalies. So let's look at an example of this. Let's actually understand what you mean when you say insert, update, and deletion anomaly. Looking at this table we have here, we have a table called teacher department, and the teacher department has the ID of the teacher, the name of the teacher, the department the teacher belongs to, and the number of subjects in that department. So that's a lot of information, right? Anyway, so as you can see, we have, for instance, Njoki, who belongs to the languages department, and data about this, which is two subjects in this department. We also have Atieno under languages, we have Chepchumba under sciences, we have Nasieku under sciences, where there's 3. So let's go on. Why is this wrong to start with? For one, let's look at insertion anomaly. It is a situation where you cannot insert data into a database without including unnecessary or unrelated information. So when you looked at our previous table, you noticed every time we had to add, let's say another teacher would repeat the same departments and the number of subjects, especially if this is a department that didn't exist before this, that did exist before this. Especially if this is a department that already existed, we are having to repeat this information on the department and the number of subjects all together, and you end up inserting redundant data for every new row. So how can we look at this? For instance, we add a new teacher called Kazungu under sciences. You can see we are adding sciences again, we're adding 3 as the number of subjects again. So this is repetitive. So every time we are having to do that, we are creating more data that we need to have, and that is an insertion anomaly. That's what an insertion anomaly is. So 2 different but related data is stored in the same table. And let's look at another way this could be an issue. So we've seen how it's an issue when we're inserting. How is it an issue when we're deleting? I put deletion instead of update next because I felt they're more related in this case. So deletion anomaly, loss of related data when some other data is deleted. So in insertion, we have an issue because we have mixed 2 different but related data in the same table. So deletion is we'll lose related data when some other data is deleted. Let's look at an example as always. When we delete all the teachers and we have our last row deleted, that means we've also lost department data. We no longer have access to the department names, the number of subjects in this department. So that's data we've lost, and that's where deletion anomaly comes in. So we've covered 2. insertion and now deletion anomaly. Let's look at update anomaly. When a change is made, it will need to be repeated everywhere. So, for instance, we stop calling the sciences department sciences, and now we call it science. That means I'll have to go through all the teachers, okay, it doesn't make sense to have 1 million teachers, but let's say it was the government managing this data and keeping track of this data. So they would have almost millions of teachers. I don't think so. That's not possible because, for instance, the population of my country is about 45 million. So it doesn't make sense for teachers to be about 1 million. But I digress. Updation anomaly. So when a change is made, it will need to be repeated everywhere. If any record is missed, we end up with inconsistent data. So not only are we needing to now look at all these teachers and then getting all the departments that are science, we also run into an error if we miss any record. So here, when we changed the sciences department to science, we had to change for Chepchumba, we had to change for Nasieku, and we had to change for Kazungu. So that's repetitive for one. And then the second thing is we ended up missing Nasieku and left it as sciences. So that introduces an issue that we didn't have where we have the wrong value in that case. So that is what we mean when you talk about update anomaly. So this is what normalization fixes for. Let's look at how normalization actually fixes this. So, for instance, the teacher department, we could split it into two tables where we have the teacher table and then we have the department table. With this, when we split it, that means when you add a new teacher, we only track maybe the department ID or the department name, just the one record here, and then we'll have a whole different table to now track details regarding the department, that is number of subjects, the office they are located in, and all that data goes in there instead of now bundling it together with the teacher data. So that's one way in which it fixes that anomaly. So it eliminates data redundancy. So how does it eliminate when it comes to insertion? We have now our teacher data on one side and then the department on the other side. We still have the same teachers. We've added a new teacher here called Kenya, and they belong to the department ID 1. So that means all you have to do is add the teacher ID, the teacher name, and the department ID. And because we already have the department ID languages already added, we don't have to do anything on the department table. We just leave it as is. And then we're working with less data in that case. I mean, we're still repeating the department ID, but we need to know the department ID somehow. So, like I said, it does not eliminate, it just minimizes it. How does it solve for deletion? If we delete all the teachers, we'll still have information on the department, as you can see. How does it solve for update? When we want to change, for instance, the sciences department to science, we only have to change it in that one place, which is the department table. And that still reflects the same information to the teacher table when you join, and we're good to go. So we have different normal forms. We have the first normal form, second normal form, third normal form, 3.5 BCNF, fourth normal form, and fifth normal form. So think of these normal forms as sort of check levels. We have different checks as we go. So we start with the most basic check, and then keep adding different checks as we go. I saw this example where they were talking about an engineer maybe designing a road, a bridge. So basics have passengers able to pass. After that, the next level may be, now can the bridge handle the load of cars? The next check may be, we can handle passengers and cars. Can we handle trucks? The next check after that may be, we need street lights installed so that this bridge is functional at night. we need checks to have, for instance, warning signs that you're approaching a bridge so that someone doesn't run over the bridge, you know, especially at night. So these are all different levels of checks. And before we get to, for instance, the lights, we need to ensure the passengers can actually use this bridge. We need to ensure cars can actually use this bridge. And we need to ensure trucks can actually use this bridge before we now get, not that this is irrelevant, but we need to start with the basics first. So think of them as that. So check level 1, check level 2, check level 3, 4, as you go. So let's look at the first normal form. What are the roles of the first normal form? So for one, each column should contain atomic values. What we mean by this is, for instance, look at the table on our left. We have Mukedi, who teaches English, and we have Mwaki, who teaches geography and biology. So we have subject with under Mwaki, we have geography and biology bundled up together. We don't want this case. We want a case where each row represents atomic values in this case. So we'll end up repeating the name Mwaki twice. Instead of having them bundled it together like that, it's better to now have this repeated twice. So we go back to the drawing board. We have teacher. We have our name Mokedi, who teaches English. We have Mwaki, who teaches geography. And then we have Mwaki again, who teaches biology. So you can have your primary key ordered differently. I had 1, 2, 3 here. Of course, here I'm treating it as a primary key, but let's ignore that part. Just understand the last part. No, like the whole idea is just track all the records. So in this case, we have a unique record where Mwaki is a geography teacher, and we have a unique record where Mwaki is a biology teacher. And all these are, so when I want to get information on the subjects that Mwaki teaches, I'm just going to query, give me instances where the teacher name is Mwaki. Or if I was not using this format of ID, where I would still have 2 and Mwaki for both the second and third instance, I would query by the ID too. But that's the whole point. So that's one rule. Each column should contain atomic values. So the next rule is each column should only contain values of the same type. Looking at the left table, we have ID of type int, name of type text, and subject. And under ID, we expect only integers. But we see Mwaki on the second row, and then name of text, we see 2 under the second row again. So we need, if we've specified the column is of type int, all the values should be of type int. If we specified its text, then all of them should be text, and so on and so forth. Let's look at the next one. Order in which data is stored does not matter in any way. So whether I start with ID 1, 3, 2, or maybe like it shouldn't matter, and this is what I mean. For instance, I want to, you can maybe add teachers by the way they are joining the school, and you can also like who joined first. So yes, you'll end up adding them, but what we mean when you say that is the order shouldn't matter. Sometimes we will have teachers who came, like looking at our example, I feel like I'm complicating with my new example. We have ID 1, 3, and then 2. It doesn't matter in the sense that it doesn't make 2 more superior in any way than 3. If we want to order by a specific way, then we do introduce an order by way of doing that in our queries. But within the table, there is no specific order. That's simply what it means. All right. So in this case, coming back to my example, looking at the table alone shouldn't tell you what teacher came first. It may give that impression, but really don't specifically design your table using that order in mind. Yes, naturally that will happen, but that's not the intention. All right, our next one, repeated groups are not permitted. So we have a table here with ID, name, subject, and subject code. So we have Mukedhi, who teaches English, subject code English. We have Mwaki, who teaches geography, subject code Geo. And we have Mwendia, who teaches geography, subject code Geo. Now let's look at back to our rule, which is repeating groups are not permitted. In this case, we now have to split it up. So have the subject table separately and then the teacher table separately. So we have Mukedhi, who teaches English, Mwaki, geography, Mwendia, geography. And then under the subject table, we have English, Eng, geography, Geo. So we're not ending up repeating geography twice because it's already uniquely in its own table. So we don't have to repeat that again as an extra record. That's what it means. And lastly, each column should be unique. So looking at our example here, we have Mukedhi, who teaches English, Mwaki, who teaches geography, and Mwaki again, who teaches geography. We shouldn't have that repeated scenario. So we should only have Mukedhi, English, Mwaki, geography, because we do want that uniqueness, and that uniqueness, those two records are the same, so we don't want those repeated values in that scenario. So that's it on first normal form. Let's look at second normal form. So for us to really follow the second normal form, we need two rules. Number one, the table should be following first normal form. Think about the bridge. And then the next thing is it shouldn't have partial dependency. So what do we mean when we say partial dependency? So partial dependency is for every non-prime attribute. These are the columns that are not part of the primary key. They must depend on the entire primary key and not just part of it. All right, so here is our example. We have subject teacher, and our primary key in this case is subject ID and teacher ID combined, because we want details on the subject ID and the teacher ID. Of course, we have the ID at the start, but the real primary key is here are subject ID and teacher ID combined. So knowing that, let's look at the other columns. We have 1 Kiswahili Nafuna. So we have the subject name tied to it, and we have the teacher name tied to it. The subject name only is determined by subject ID, and teacher name is only determined by teacher ID. So we have a case where we have primary key attributes determined by not the full primary key. In this case, a combination of subject ID and teacher ID. That's what we mean when you talk about partial dependency. So in this case, we do have a case of partial dependency because it's partially depending on the primary key instead of fully depending on the primary key, like all the other columns depending on the primary key. So how do we solve for this? We split it up. So we have your subject teacher table, which will only contain subject ID and teacher ID, and that's our primary key. And then we'll have our subject table separately, which will have details regarding the subject. That is your subject ID and your subject name. And then we'll have our teacher table, which will contain the teacher ID and the teacher name. And that's it on second normal form. Let's look at third normal form. We do have two rules for this. We have that it should follow the second normal form, the bridge. I'll keep referencing the bridge. Closure. Anyway, and it shouldn't have transitive dependency. So what do we mean when we talk about transitive dependency? Every non-prime attribute, those are the columns that are not part of the primary key, must depend directly on primary key. So we shouldn't have cases where one column that is not a primary key, depending on another column, not a primary key. They should only depend directly on the primary key. So let's look at an example. We have subject ID, department name, and subject name. Before we continue, our primary key here is subject ID only. This is a subject table. So all the column values should be dependent on subject ID only. So our first instance, we have subject ID 1 from department 2, and then we end up getting the department name, which is related to department ID and not in any way affiliated to subject ID, and the subject name. And then the second value, we have 2, department ID 5, we have the department name, technical, agriculture, and again computer. So we have a case where a non-primary key attribute is depending on another non-primary key attribute. That's what we mean when we talk about transitive dependency. So to eliminate this is what we do. We have a whole different table where we have details for that like those details that are depending on each other. So in this case, department and department name, and then subject on its own, where we'll have the subject details, the department ID, and the subject name. And that's how we solve for transitive dependency. And that's it on that normal form. Let's look at our next one, which is BCNF. So what is BCNF? It's also called the Boyce-Codd normal form, also called 3.5 normal form. So 3.5 in that it is just more stringent than 3. So we've checked that 3 covers for transitive dependency. So now this just goes a step further, and we'll see what this step further means. Of course, we need to follow the third normal form before we go higher. And then after that, this is the other rule. For every functional dependency, X determines Y, which means Y is dependent on X. X should be the super key of table over table. So when X, column X, determines column Y, like Y is dependent on column X, X, which is the one determining, should be the super key of a table. So let's look at what we mean. We have student subject here, which is our table, and I need to specify here the primary key is student and subject, because we're tracking details regarding the student and the subject. So let's look further. We have Kendi, agriculture, and Zawadi as a teacher name for this subject and for this student. We also have Mukami, biology. The teacher name is Fatuma. We have Linda, music. The teacher name is Kazungu. We have yada yada yada. So in this case, as we can see, student and subject combined, which are the primary keys, do determine the teacher name. But something else, the teacher name does determine the subject, because we don't expect a teacher who doesn't teach the subject to be teaching us as the subject. So in this case, the teacher, which is a non-primary key attribute, is determining key attributes. So it's determining the subject. That's what we're trying to avoid. We shouldn't have that. So how do we fix for that? This is what we do. We have student subject separately, and then we have subject teacher name separately. So this is what we'll end up with. Look at the table, pause and look at the details. We have Kendi, Mukami, Linda, Luna, Mamba doing those subjects, and then the different subjects and the different teachers that teach those subjects. As you can see, we have music coming twice with 2 teachers that are Kazungu and Waridi. So that's how you solve for it. That's how you solve for BCNF. And that's it on BCNF. Let's look at the final one, which is 4NF. I said these are the final one. There is another one after that, which is the fifth normal form. I'm not going to cover that. I don't think it's used that often. So I'm just going to end it at fourth normal form. Anyway, so fourth normal form follows the BCNF normal form. So before you go to 4, you have to pass through 3.5. And apart from that, the other rule is it should not have multi-valued dependency. What do we mean when we say this? With this, it eliminates independent many-to-one relationships between columns. And 2, a given table may not contain more than one multi-valued attributes. Alright, so 2 things: eliminates independent many-to-one relationships between columns, and a given table may not contain more than one multi-valued attributes. Let's look at our last example. We have a table that tracks student, subject, and activity. And for this, our primary keys are the combination of these 3 attributes: student, subject, and activity. So we are ending up repeating a lot of records because we want the primary key should be unique. So the uniqueness is derived by a combination of the 3 columns. So we have Wangoi, who does music and also does hockey. But Wangoi also does Kiswahili and also does drama. But because Wangoi does music, she also does drama, so we need to track that. And Wangoi does Kiswahili and also hockey. So these end up being 4 different rows. We could have avoided that. And of course, Wanja, who does Kiswahili and hockey. These are just other examples. We're not showing that repetitiveness. And Moedera, who does mathematics and netball. So we are seeing this repetitiveness where we're now combining so many different values together so that we end up having uniqueness and repeating these as we go. How do we solve for this? Something that someone mentioned when talking about the fourth normal form is when solving for it. So this rule actually applies for more than 2 columns. So here we have 3 columns. I say this because to solve this, we'll still have repeated combinations, but at least it will only be for 2 columns, not 3 columns. So more than 2 columns in this case. So 3 and above. So to solve for this, we'll split it into 2, and we'll have 2, one for student activity and one for student subject. We can see Wangoi is repeated still, but this case it's only repeated twice for 2 unique combinations. So Wangoi and hockey and Wangoi and drama. And when it comes to subject, we have Wangoi and music and Wangoi and Kiswahili. And of course, Wangoi hockey, Wanja hockey, Moedera netball, and Wanja Kiswahili, Moedera mathematics. And that's it when it comes to normalization in databases. I hope you've learned a lot, and I hope you practice this when you're designing your ER diagrams, when you're designing your databases, and happy coding. All the best, and from all of us, which is me, from Kodarasa, I wish you a good tidings, good life, a good day, afternoon, night, good evening. Anyway, from all of us at Kodarasa, me, have the best time, and until next time, happy learning. Bye. Thank you.